All right, so the next kind of preferences we're going to look at are these quasi-linear preferences. So we're going to talk a little bit about the solution technique, which is really similar to the well-behaved ones, and then do a quick numerical example that we didn't get to in class last week. All right, so remember these utility functions are kind of like max, whatever your utility function is, for example, like ln x1 plus x2 subject to p1 x1 plus p2 x2 equals m. So like it's quasi-linear. So it's linear in x2 here and non-linear in x1. It could be linear in x1 and non-linear in x2, but it's linear in one of the goods and non-linear in the other is kind of the hallmark of these ones. And what these difference curves look like are kind of these like vertical mirror images of each other. And they have this kind of property that once your income is above a certain level, in this case, like you're going to buy a certain amount of good one, and as your income increases, you're still going to buy the same amount of good one, as long as your income is above some level. That's just due to like the nature of these, and the tangency is going to exist at like the same place vertically. And we kind of talked about that in class, and you can review those other videos if you want a review of those or of that property. So the solution technique here, so these are obviously like pretty easy to identify. Like it will say quasi-linear. You can just look at the utility function. You can see that it's quasi-linear. It's essentially going to be the same as well-behaved preferences. So if you haven't watched that well-behaved preferences video, you can go back and watch that. But you can use like the MRS condition technique, or you can use the Lagrangian here. But same two techniques, or three if you count unconstrained maximization, like the same techniques that work for well-behaved preferences work for these kind of preferences. The key though is that we have to just be careful about corner solutions. Have to watch out for corner solutions. So what I mean by that is like really all we have to do is like use one of these solution techniques, and if you get like an answer that doesn't make sense, like you're going to consume a negative amount of one of these two goods, all it means is you consume 0 of that good and spend your whole budget on the other good. So for example, if you solve and find, x whatever 2 is less than 0, all this means is x2 star actually equals 0, and x1 star is going to equal, spending our whole budget on it. And same with the other way around, right? If you got x1 is less than 0, it just means x1 star is equal to 0, and you spend your whole budget on good 2. But essentially, like the solution technique is the same. We just have to watch out for these corner solutions, because we could have solutions where we consume no x1 or no x2, depending on like the slope of the budget constraint here, or how much our income is basically. So let's go through an example where we can kind of see an interior solution to this, and then we can see a corner solution, and that's due to like our income not being high enough. Okay, so I'm not spending that much time on these solution techniques, because it is the exact same kind of way as we solve well-behaved ones. So just watch that video, and I kind of describe these techniques. We can apply those same things to these types of problems. So Monty Don of BBC fame is an avid gardener. His favorite plants are tulips and hydrangeas. His quasi-linear utility function is the following. So you can see it says it's quasi-linear right away, so that's helpful, but you can also just see it's non-linear in H and linear in T, where T is the number of tulips and H is the number of hydrangeas in his garden. So he has 500 square feet for his garden. Each tulip takes up 1 square foot, and each hydrangea takes up 4 square feet. He gets both kind of plants for free, so he just has all these plants sitting around. So it's basically his budget constraint is about how much room he has in his garden to plant these things. If you wanted to maximize his utility, how many tulips should he plant in his garden? What about hydrangeas? Okay, so I'm just going to give myself some room here. We can write down the maximization problem. Okay, so the problem is to maximize this function, this utility function, minus h squared, subject to the budget constraint, where each tulip takes up 1. So the price of a tulip, this quote unquote price of a tulip is 1 square foot, and the price of a hydrangea is 4, and he has 500 square feet. So here's our problem, and we're trying to pick t and h to maximize this function, right? All right, so we can use, Lagrangian or MRS condition. I'm going to use the MRS condition again. So remember, this is where the MRS, the first equation is the MRS equals the price ratio, so I'll put T and H here. And the second one is where we're spending our whole budget. So let's work on this MRS condition here. I'll just do it on the other side here. So remember, the MRS is the negative of the margin utility, and here it's T over the margin utility of H equals the negative of the price ratio. So here that's negative 1 over 4. So you can take the margin utility with respect to T as just a 1. Yes, we'll put a negative there that it's going to cancel out in a second. And with respect to H is 100 minus 2 times H, right? Equals negative 1 over 4. We can get rid of the 2 negative signs. I'm just going to work my way down now. So 4 equals 100 minus 2 times H, just cross multiplying. 2H, let's keep it lowercase, I guess, equals 96. So H equals 48, H star. So notice that with these quasi-linear utility functions, like the amount of tulips, the amount of hydrangeas this person wants to buy is not like a function of income. Like we could just with this first equation solve for the number of hydrangeas. Like we didn't need to plug it into our budget constraint or anything. It does not depend on income. So we could just solve it right away. So that's like a particular feature of these utility functions, and we can plug this into our budget constraint to figure out into budget constraint. I'm going to say BC for budget constraint to find T star. And so in this case, T star plus 4 times H star equals 500. T star plus 4 times 48 equals 500. And so in this case, T star equals 308 if we solve that. So here are 2 optimal amounts of hydrangeas and tulips. We have numbers for prices and income, so you can actually get quantity demanded for those particular prices and income, and we get, no matter what, he wants to plant 48 hydrangeas, and now he's going to plant 308 tulips in the rest of his garden. Okay, so this was like an interior solution, right? Because we're planting some of each. Now let's look at what happens when his garden shrinks. So now it's only 144 feet. So it's going to be the same problem, but he only has 144 feet to plant these 2 flowers. All right, so I'm just going to give myself a little bit of room here. We can write down the problem again if you want. Getting my pen out here. So the problem is to maximize, sorry, my dog is really interested in what's happening outside, is to maximize this utility function again, which is T plus 100h minus h squared, I believe. But now the new constraint, the price of tulips, the room it takes to plant them is still 1. It's still 4 for hydrangeas. But we only have 144 square feet to plant where we used to have 500. So it's really just like this part that's changing. So we can again use the MRS condition. And really nothing is going to change. Oops, condition. That's the solution technique I'm going to use, but you can use Lagrangian as well. But really nothing's going to change in this part that we solved for before, right? Because like the square feet of the garden did not enter into that. So we're going to still get that he wants to plant 48 hydrangeas because nothing's changing here. I mean, I can write it out, but nothing's going to change. So the MRS condition is 1 over 100 minus 2h equals 1 over 4. I guess there's negative signs on both, but they're going to go away. And if we do this, we're going to get h star, I'm going to say h because we're going to have to go back and correct this, but h equals 48 is what we get. Now we can do exactly what we did before when we plug this into our budget. So now we have t plus 4 feet per hydrangeas times 48 equals 144. This is our budget constraint. But notice when we try to solve for t here, we're going to get a negative amount. We're going to get t equals negative 48. Like this is, we can't plant a negative amount of tulips. It makes no sense, right? This is not possible. And so this is your key to kind of seeing. As soon as you see this negative sign, it's telling you, no, this is a corner solution. And so what it's saying is that like t star actually equals 0. And h star is going to be planting only hydrangeas. So we have 144 square feet. That's our income. This is the price. And so we're actually going to plant 36 hydrangeas. So here's an example of when you get a corner solution. Like our income isn't high enough or our garden isn't big enough in this case to plant both of these flowers. And so what you're going to get is this kind of nonsensical answer where you're consuming a negative or planting a negative amount of tulips. And as soon as you see this, you're like, okay, the optimal amount of that good is 0, and we spend our whole budget on the other good. We actually don't have enough room in the garden to plant 48, so we just plant 36, and we're going to only plant hydrangeas. So in order to plant both tulips and hydrangeas, how big does the garden need to be? Carefully explain. Well, we already saw that no matter what, he wants to plant 48 hydrangeas, right? We can see that from just this solution. Before we plant any tulips, we want to plant 48 hydrangeas. So always wants to plant 48 hydrangeas. So a garden would need to be 192 feet. This is the size of the garden required. To plant 48 hydrangeas. And so the garden needs to be bigger than that, or the income needs to be bigger than that in order to want to plant tulips as well. So the garden needs to be greater than 192 square feet to plant both flowers. Because as his income goes up, he's only going to plant, or how his garden gets bigger and bigger, I guess in this case, he's only going to plant hydrangeas until he plants 48 hydrangeas. Then he's going to start to use the rest of his garden on tulips. If his garden is smaller or equal to 192 square feet, he's only going to plant hydrangeas because he wants, no matter what, 48 of them before he even thinks about planting tulips. Okay, so that's like the key with these quasi-linear preferences. We can solve them the exact same way as these well-behaved preferences. We just have to watch for these corner solutions. So here we had a nice interior solution where he planted both types of flowers. Here we could see that we got like a negative amount of tulips, which obviously makes no sense. So he's going to plant 0 tulips and just use whatever room in his garden he has to plant hydrangeas. And he can only plant 36 of them. And he'd keep increasing the number of hydrangeas he's going to plant until he gets 48 hydrangeas if he has a garden of 192 square feet. And as soon as his garden's bigger than 192 square feet, he's going to use all this extra room to just plant tulips in this case. Okay, so hopefully that's helpful to figure out how to solve nonlinear preferences or nonlinear utility functions, or utility functions represent nonlinear utility functions or quasi-linear utility functions that represent certain kind of preferences.